Welcome to the fourth lecture, which is Supervisory Control and Data Acquisition, also known as Scada systems. So before we move into get the overall picture of the Scada system, so let's take a look at the five-layer structure of the industrial automation network. As you can see here, we have five layers. Starting from the first layer, which is the field devices. They could be sensors, actuators, so on. Some could provide the data as 4 to 20 milliamps signal or 0 to 10 volts voltage signal. Sometimes they could communicate using some sort of communication methods like RS-232 or RS-485 or Ethernet, and then it goes to the I/O level. So I/O level is the input-output interface, which gets all the data from the field devices, and then it goes to the control level. Control level is the logic level, which basically the processors which runs the programs, and this the I/O level basically the input-output interface or the cards of a PLC, and this is the PLC core which runs the program. And then we move to the supervisory level, where you have the SCADA system or HMIs, and all the things are on the supervisory level. So where you can monitor the overall plant processes and variables from the SCADA system. It doesn't need to be a HMI, so the SCADA is different to the HMI, but SCADA has a lot of more functionalities compared to a single HMI, which is connected to a machine. And then you have the fifth level, which is the enterprise level, where your managerial level take the all the decisions based on the data available to them. As you already know, that the SCADA stand for Supervisory Control and Data Acquisition. So it's all the functions, supervisory, control, and data acquisitions are embedded in a SCADA system. The term refers to a system that combines the software and hardware, and enabling industrial organizations and factories to control process and equipment. So the SCADA's function is to combining the software and hardware and enabling the industrial environment to control the process and monitor the processes. So the major function of the SCADA is to acquiring the data or collecting the data from remote devices. It could be input-output devices or data coming from PLC. And so those data will be displayed on the SCADA software platform. SCADA operators and supervisors then use this data to monitor processes. So there is different teams of people who is operating this SCADA system, who are the plant operators and supervisors, sitting in a central control room, so they can observe all the parameters coming to the SCADA software interface. And by looking at this data, they can maintain and improve the efficiencies, improve the quality of and the profitability of the product, and they can identify the problems and emergencies, and the SCADA produce alarms, so they can visualize what sort of alarms are coming. And SCADA host platform also provide functions for graphical displays, like I mentioned, alarming, trending, and sometimes you can record the data over a period of time. So SCADA is used in the oil and gas production and plant factory automation, wastewater treatment, food and beverage, and even in electrical power plants, and also in traffic light. There could be many more applications, but to name a few, these could be generic applications.
A Scada system is a collection of both software and hardware components that allow supervision and control of plants both locally and remotely. The Scada also examines, collects, and processes data in real time. Human-machine interface, or HMI software, facilitates interaction with field devices such as pumps, valves, motors, sensors, etc. Also within the Scada software is the ability to log data for historical purposes. The structural design of a standard Scada system starts with remote terminal units, or RTUs, and/or programmable logic controllers, or PLCs. As you know, RTUs and PLCs are microprocessors that communicate and interact with field devices such as valves, pumps, and HMIs. That communication data is routed from the processors to the Scada computers, where the software interprets and displays the data, allowing for operators to analyze and react to system events. Before Scada, plant personnel had to monitor and control industrial processes via selector switches, push buttons, and dials for analog signals. This meant that plants had to maintain personnel on site during production in order to control the processes. As manufacturing grew and sites became more remote in nature, relays and timers were used to assist in the supervision and control of processes. With these devices employed, fewer plant personnel were required to be on site in order to oversee and control operations. While relays and timers did provide some level of automation, the panels required for these devices took up valuable real estate. Troubleshooting was a nightmare, and reconfiguring was difficult at best. These issues, in conjunction with the need to grow even larger industrial plants, helped to facilitate the birth of automation. As you may know from previous videos, controlling industrial plants via processors became a reality in the 1950s. Gas and oil, utilities, and manufacturing were major users of these new technologies and supervisory control. About a decade later, telemetry came on the scene to offer even more remote capabilities, with automated communication and data transmission to remote monitoring locations. Another decade later, the term Scada was used to describe systems with PLCs and microprocessors that were being used for the monitoring and control of automated processes on an even greater scale than ever before. Scada, back then, was anything but practical. They were colossal machines, mainframes really, and since networking was not yet in the picture, they were standalone units. In the next couple of decades, the 80s and 90s, with computer systems getting smaller, the advent of local area networking or LAN, and HMI software, Scada systems were able to connect to related systems. Unfortunately, though, the communications were typically proprietary, which meant that connections outside of the particular vendor of the Scada system were not allowed. This early Scada was coined distributed Scada systems. Later, in the 90s and 2000s, Scada began to implement open system architectures, with communication protocols that were not vendor-specific. As you can imagine, this opened up Scada's ability to connect with varying vendors. This newer, more improved Scada was then called a networked Scada system. Newer and improved Scada, unfortunately, didn't last long. With computer technology growing rapidly, IT development quickly gathered steam. The default database for IT became Structured Query Language, or SQL databases. Scada developers didn't implement these standard databases, so Scada became out of date rather quickly when other technologies so rapidly changed. Current-day Scada systems have adapted to the changing technologies and have a great advantage over the older Scada systems. With the adoption of modern IT standards such as SQL and web-based applications, today's Scada allows for real-time plant information to be accessed from anywhere around the world. Having this data at the operator's fingertips facilitates improved plant operations, allowing for responses to Scada system queues based on field-collected data and system analysis. These operator interactions can be from a computer right on the plant floor to an office building in some other region in the world. Advancing technologies have indeed made the world seem like a very small place, relatively speaking. And because the current Scada system software has typically adopted the SQL database model, historical collection of data may be logged and used in trending applications to further improve plant processes, as well as creating mandated record keeping for some of the industries out there. Essentially, Scada is a collection of hardware and software components. This collection of components begins with real-time data collected from plant floor devices such as pumps, valves, and transmitters. These components don't have to be from a particular vendor. They just need to have a communication protocol that the processor can utilize. Data collected from the field devices is then passed to the processors, such as PLCs. From the processor, the data is distributed to a system of network devices. These devices may be HMIs, end-user computers, and servers. On the HMI and end-user computer, graphical representations of the operations exist for operator interactions, such as running pumps and opening valves. This data may also be analyzed and used to enhance plant production and troubleshoot problems.
Now we can see the components of a SCADA system. So there are a few components. If you take a look at the overall picture of the SCADA system, first one you will see in a plant or industrial environment is the field instrumentations. That includes the feedback sensors, limit switches, valves, pumps, and all the things. And instrument is also required to function in a harsh environment, which means like you have to deal these devices has to deal extremely hot or cold environment, dust, or whatever the harsh environment in the industrial field. Then these field devices are connected to a PLC or RTU. PLC, like the programmable logic controller, and RTU stand for remote terminal units. The only difference between the PLC and RTU is has the embedded communication capability compared to a PLC, which is they can transmit the data via different kind of communications. Sometimes it could be wireless communication. So it has the capability of a computer and the same I/O compatibility as a PLC. So then you have the communication link, so where the PLCs and RTUs are linked to the Scada host platform. So it could be a Modbus, Ethernet, or radio, or like unguided media. So dial-up or dial-up lines, so on. So finally, we have the SCADA host, which is shown in this picture. So you have the central computer station, including HMI software. HMI stands for Human Machine Interface, and so it has all the dashboards or screens used to control machinery. Line operators, managers, and supervisors in the industry rely on HMI to translate the complex data into useful information. So anyone who is operating this SCADA platform can visualize the data coming to this SCADA host platform using via these communication links. So the operator's responsibility is to monitor, maintain, and engineer processes of the SCADA elements. And the accounting, maintenance, management, and material purchasing equipments and are performed or are partly performed from the data derived from the SCADA system. So you can generate historical data, so that could be then later can be used by the management in order for their purchasing and prediction and planning of the production. So IT or information technology is traditionally separated from Scada, as you have seen in the previous video. But now in the most developed Scada systems, IT is used. You have databases, networks, and all the things that you can access to your data. So the Scala has different functionalities. The first one is acquisition and processing data. And you can remote control, which means like you're from anywhere in the world or anywhere outside your plant. You can control the process variable through the RTUs and PLCs. And SCADA can generate alarms based on like if some sort of variable over go beyond a threshold level, and then it could be programmed to generate an alarm. And you can save the data, which is historical data or archive data, and it has a human machine interface, which means that like you can monitor the data and you can control from the HMI, and you have the ability to emergency control of switches in the case of emergency situation, and also you can do the demand side management as well. SCADA systems developed so far by passing 4 generations. So the first generation was the early or monolithic SCADA system. So that was independent and non-connected, not connected to other systems. So it's like a remote system. So networks are generally not non-existent, and each centralized system stood alone. And the limited their scope to tasks like monitoring sensors and flagging emergencies. So you can't control your system or the plant using any other platform which is a remote location. So the only like a local system, you can control your system by locally. And then distributed SCADA system came, which is the second generation. So it took the advantage of local area network, and the information was shared across the stations in real time. So each station had their own task. Distribution increased the processing power and redundancy of the system. And later the network SCADA system came, which is the third generation. So it could communicate through phones or data lines with fiber optics or Ethernet to transmit data. So the speed of the SCADA system developed rapidly. You can communicate and control a plant remotely uh, thanks to the fast communication infrastructures like fiber optics and Ethernet. Currently, we are now experiencing and moving towards the Internet of Things, or which is the fourth generation of the SCADA system. So now the scale is capable of IoT databases and real-time monitoring of the data and controlling via the internet. SCADA system is different to HMI. HMI stands for Human Machine Interface, and which means the engagement of a human with the machines to control and monitor the data. An HMI works by connecting an operator to a system, devices, and all machines via a screen or dashboard, rather than just displaying the data, which can be difficult to analyze quickly and easily. Information is presented visually, often in the forms of graphs, illustration, and photographs. So HMI basically, like you have when you're connecting a PLC, and if you want to control different parameters, inputs, and you want to visualize different outputs, so you might need a large number of input and output cards. So in that case, the HMI reduces that burden because you can by putting like switches and output indicators on the HMI itself, reducing the burden of having large number of inputs and outputs where the operator can feed and get the data from a PLC. So from the HMI, so it is quick and easy to evaluate the data from different machines, process, and locations. Examples of HMIs are machines with touch displays and mobile devices or an alarm. You might have seen the HMI displays even in our laboratory environment. So the HMIs are typically equipment machines or work self-focused. So you just connect a single equipment or PLC or machines to a HMI display. Their perspective is limited in scope to the immediate area, whereas the Scada typically takes a wide view of the operation. So you have a number of different machines or the PLCs. You can visualize your all data in one single platform. So the from the Scada you can monitor the piece of equipment, entire plants or processes or multiple work cells in a single Scada host environment. Some HMI design software can be as like Scada, but you can't use HMI as Scada, but some HMI design softwares can be used as like Scada, but opposite that most Scada can be used as a HMI.
So, let's dive into Scada for now. Scada stands for Supervisory Control and Data Acquisition. These are used for monitoring and controlling large areas, typically a full site or plant. Scada systems are a combination of many systems, including sensors, RTUs, or remote terminal units, and PLCs. Data from all of these systems is then sent to the central Scada unit. That Scada unit has its own HMI. This is why a lot of people get confused and think Scada and HMI are one and the same. That HMI, or Human-Machine Interface Unit, on the Scada can monitor and control anything that is connected to it. In conclusion, HMI can be part of Scada, but Scada cannot be part of an HMI. It's that simple. So let's talk about a common use for Scada that I have personally encountered. While working for a water and wastewater treatment facility, I encountered a Scada system. The HMI was located at the main water plant building. This HMI was connected to the main Scada unit at the water plant. Each booster pump station within the water district was represented on the screen. At each location, there was a PLC that was connected to some sensors to monitor water flow, pressure, and other things, and it was able to run and control the pump itself. The remote Scada unit was connected to the PLC system and allowed operators to control and monitor each pump station from the main plant. I'm sure you can imagine how much time and labor a good Scada system can save a company. I like to think of a Scada system kind of like a modern vehicle. You have several different sensors connected to different computers on board. Most of your interior features like motorized seats, climate control, and other things are controlled by a BCM, or Body Control Module. Most of your engine functions and sensors are monitored and controlled by your ECM, or Engine Control Module. These modules all send information to a main screen in your dash for you to see and control through driver controls, which is essentially your HMI. An HMI is essentially a user control station, usually in the form of a touch screen or a screen with some buttons attached. They are typically tied to a machine or process. Most HMI applications have the screen tied to a PLC that it is compatible with. Certain functions and sensors can be programmed to monitor and control on the screen itself. Be sure to check out our RealParse video on HMIs. So what did we learn today? Hopefully, you now know the difference between a Scada and HMI. They are different but can be used together to create a very functional and useful industrial tool. A Scada system is comprised of remote systems all tied together at one central hub. Our example was the water treatment pumps that were located all over a water district. They were able to be controlled and monitored from a central location at the water plant. An HMI is an interface for humans to monitor and control a machine. Even our Scada systems will typically involve an HMI. HMIs are usually connected to one machine or process and are able to monitor and control certain functions of that machine or process.
SCADA systems use different kind of methods for transmitting the data from one machine or PLC to a SCADA host software. So the transmission modes could be Ethernet, radio waves, GSM, or rented telephone lines. But the transmission media, that could be the twisted bare metallic cable, coaxial cable, fiber optics, satellite communication with telephone lines, or radio frequencies, which could be like guided and unguided media. So SCADA also use software. So the SCADA software you have to buy from the vendors. SCADA software is basically receives the data collected from the devices through the PLCs or RTUs and processes. The data is then displayed on the screens and dashboards, often in animated graphs, diagrams, and images, so that the operators know in real time what is happening on the floor or in the field. The operator can analyze this data, determine whether the operations are running optimally and whether there need adjustments or urgent intervention. Examples of operators can use the SCADA system to change rates on settings, recalibrate equipment, and shut down or process altogether if necessary. So basically, you can monitor and control your devices on a factory using the SCADA software. Basically, not a single machine, so not large number of machineries and controllers you can take a look at from a single platform. So some SCADA software vendors are Siemens. They have the Symmetric SCADA, and the Rockwell Automation sells the factory top SCADA software, and Schneider Electric has the Avena software. So this is how it looks like in SCADA systems in a power plant. So these are the operator's view, and you can visualize all the parameters in a graphical way, how they are operating. So like any system, this SCADA also needs a security in order to protect the system from fraud. And internal networks are used for all corporate communications. So that is a huge risk even in SCADA. So they are vulnerable for many threats due to this TCP/IP based systems. So the attacks could be denial of service, DOS attack, which crashes the SCADA server or shut down the system. Sometimes the SCADA attacks could be to delete the system files, or that could lead to system downtime and loss of operation. Or SCADA attackers sometimes use Trojan, which means like putting a different kind of sort of work, and inside the work there's a virus that could take the control complete of the system, and then they can take the advantage over your control and can get this control system run by themselves. So developing an appropriate SCADA security strategy involves analysis of multiple layers of the both corporate networks and SCADA architectures. So that includes firewalls, proxy servers, operating systems, application system layers, communications and policy and procedures. So the strategies for Scada security should be complement with the security measures implemented to keep the corporate network security. So Scada security is a different topic, but make sure if you have a Scada system, it is secured from outside threats. Now, Scada and the DCS. DCS stand for Distributed Control Systems. So that is DCS is a older version before came the SCADA systems. So still some factories and process control use DCS systems, which has some sort of advantages over SCADA. But if you take a look at these distributed control systems, so that is also has your input outputs or the field level devices and connecting to the programmable logic controllers or RTUs, and then you're having a HMI system running. And the advantage of DCS over SCADA is like you can visualize what is happening on all these these PLCs, and there could be a one platform you can burn the control. You can write the code and you can edit the code of any PLC, and you can just download the code to any of the PLC which is connected to your communication link, and also you can control and monitor the data. So DCS might be slower compared to the SCADA, and DCS is an older version compared to the SCADA. Nowadays DCS is replaced by the SCADA systems. The only advantage in its DCS is you can just write the program for each of the controllers, and then from a centralized computer, and then you can upload or download the code to the controller.
While this was, at
So
least in
we
the
can
earlier
just
days,
take a look
more
at the
cumbersome in
difference
the
between
SCADA
a SCADA and a
implementation,
DCS
the
system from
DCS
this
had
video.
many predefined functions that could be customized and deployed for various applications. This didn't eliminate the need to write code. However, it did help to facilitate faster integration because less time would be spent writing code for commonly used functions. Processing times are somewhat slower in the DCS versus the PLC RTU SCADA environment. While this is not necessarily problematic, it could have an impact on processes that are very time-sensitive. Communications within a SCADA system can vary widely and have adapted to the changing technologies. While the DCS has also adapted, there are still some proprietary communications that can be challenging. It has been said that if safety is a priority, then the DCS is the route to go. However, nowadays, with the abundance of safety processors, a SCADA system may also be selected. To sum things up, in today's market, there are not massive differences in the systems. DCSs have integrated operator interface software with tagged databases, while SCADA requires you to purchase additional software and build or import your tags. If you have a very time-sensitive process, SCADA systems may have a slight advantage, as the processing time is faster. Need an open communication architecture? Advantage SCADA. Concerned about safety? Advantage DCS. As you can see, there are a lot of similarities between the two systems. Either way you go, hopefully this video has shed some light on both the similarities and differences between the two systems.